When I was a young lad, I used to belong to the Boy Scouts. And every summer, one of the highlights of my holidays was to go on a scout camp. One of the greatest challenges for the young scouts was to see how few matches they could use to light a campfire or a bonfire. If you could use 2 or 3 matches to light a bonfire, you were considered to be an expert. If you could use just 1 match, you were considered to be a grand master. I used to use no matches. Now, the campfire, the bonfire which we have burning here this evening, of course, is part of an ancient human tradition. Indeed, our ability to make fire at our own will, etc., using our own techniques, is one of the greatest achievements of early human civilization. 10,000, 50,000 years ago, certainly a very, very long time ago. And today, of course, I wanted to talk about primarily the chemistry of how wood fires burn, but also about the physics and the sociology. So I'm going to start off by telling you that when wood burns, it's actually, when you're lighting fire and burning wood, you are actually not burning the wood. That is going to be the whole point of my demonstration this evening. And I wanted to start off by showing you how it is possible to ignite. I have here a propane burner, and how we ignite a propane burner. Oh, by the way, before we go on, I do have something I wanted to do, and that's just to ignite one of I have a little spirit burner here, and I'll tell you about why I'm igniting this, because it's very, very relevant to our topic. So I'm just going to put that flame there. And then I wanted to tell you that when we have, going back to a modern gas burner like this, you see, it's very easy to set the gas on fire. And the reason is you press a little thing, and you can all see a tiny little piezoelectric spark. So if you want to set this on fire, you simply turn on your flow of gas here, press the spark, and bingo. We have a wonderful flame, and it's alight straight away, you see. And we know that the propane is burning directly because it has come there. However, if I wanted to show you now, I'm going to set fire to this piece of wood, and if I hold this wood in our, let's say, flame here, you can see the wood is not catching fire. And furthermore, you can probably understand that if I wanted this wood to catch fire, it would take a very, very long time indeed. And the reason why this is the case, it hasn't even just started to char, the reason why it takes so very long indeed, because actually the wood chemically changes into a whole range of different substances when it actually burns. And this is what I'm going to demonstrate for you today. I'm going to start off by showing you, I have here some sawdust. Sawdust is basically small pieces, tiny, tiny pieces of wood. They have a large surface area. You can see they're smoldering a little bit as I drop them onto our fire, which is burning. So this is wood which has been powdered to a very, very high level, and I've placed it in this retort flask here. Now, a retort flask is one of the most ancient pieces of apparatus, chemical apparatus that the human being has invented. And I'm going to, and it is used primarily for heating a substance and then collecting any vapors that might come off from that substance. And so what I'm going to do now is to heat this up, this wood in here, and let's see if it catches fire inside the flask. I'm going to heat it with a very, very strong flame indeed. So allow me to turn the gas on, turn on our thing here, and I will now commence this process. Now, this experiment, which I'm going to demonstrate, this process which I'm demonstrating for you now, is going to take approximately 10 minutes. It's quite a long process, and we're going to observe the gradual changes that take place to the wood as it is being roasted by my very, very hot flame. Now, I hope you can already see that there is a little bit of steam, condensate, collecting on the inside, on the top of the flask, and indeed you can all now see that there is some smoke coming out of the bottom of the flask. Furthermore, you can now see more smoke, and then those of you who can see, there is some charring of the wood, etc. But, and you can also probably see that the flask is glowing red hot, and yet the wood inside is not catching fire, dear children. Let's see now, we'll carry on this heating process, and we'll explain to you a little bit about what wood actually is made of. I'm sure you will all agree that at this very, I'm going to put a light here to see, oh, can you see that? It's burning. Now, that's not the wood it's burning. It is actually a product of this chemical reaction which I'm doing here, which I'm undertaking here. And also you see that not only is that gas burning there, but there is also a liquid dripping out of the bottom of the flask. Now, if you don't mind, I'm going to come round and with my back to you just to warm this up a little bit from the front. Please excuse me. And I'm sure you'll all agree that we are now burning, where the wood is not burning directly, but it has been chemically changed into different substances. And those different substances are now in the form of two different states of matter. There is a gas which is being produced here in the form of a smoke. And furthermore, there is a liquid, an orange gooey, smelly liquid, which is coming out of the bottom. Furthermore, you may observe that there is on the side of the flask a dark brown, oily liquid, which is going down the side of the flask. So what I'm demonstrating for you is a type of a chemical reaction in which we take the wood, which is made of, I'll tell you very shortly what it's made of, and we are breaking it down into smaller particles. I'll just see if we can get that to light again. It burns sometimes, sometimes it doesn't burn. But the point is, the wood is being chemically changed. And I wanted to tell you in this very crude type of experiment, and can I also tell you, this type of experiment has been done for thousands of years. Not because people wanted to see what happens, because it had a utilitarian purpose, and that was to make charcoal. You'll notice already at the bottom of this flask that we have essentially a black solid, which is in fact charcoal. I am now going to try and set fire to it once again. Excuse me while I do wander around a little bit. And many of you will be able to see the tar, the sort of, whoops-a-daisy. These splints are not very good. I tried to get one out. I'm multitasking, as you can see, reasonably successfully, if I may say so. Now, let's just put let's put this, I do love these fires. You must excuse me. I'm a bit of a pyromaniac. I'm just trying to get enough of the products to be able to explain to you what is actually going on. Now, you see, there it is. And I think that basically that's enough to show you that wood, when strongly heated, it can change. I'm going to turn off my flame now. Whoops-a-daisy, let's get it turning in the right direction. I think I've got it in the right direction. Yes, that's turned it off. Now, please look at this, splendid. The wood is producing a dense smoke, and it is producing a liquid there. So wood here is a solid. We're talking about the states of matter. Here it is like this, and we have heated it very strongly. Now that heating process is the same heating process, of course, when we put a splint into a flame and it catches fire instantaneously. Well, not quite instantaneously, because before it catches fire, it always must char. It must have a little bit of blackness on it, a little bit of black charcoal. And once it's got a bit of black charcoal, we're then in the position, what we're actually doing, we're producing this smoky stuff here, which is in the gas phase, and we're producing this very, very, very smelly liquid here, which, can you see, it's an oily color, it's got some dark oily droplets in it, and it's suspended in a sort of a light orangey type of watery layer. And we have furthermore left behind here some charcoal. So what we have done by applying the process of heat, we have converted wood, which is a solid, into three completely different substances. One of them is at three different states of matter, should I say, three states of matter. One of them is a gas, one of them is a liquid, and one of them is a solid. And each of those three states of matter is no longer the same as the wood which it started off as. As I told you, this process has been practiced for many, many thousands of years, primarily to make charcoal, which I'll be talking about later, but also to make this liquid here, which is called a pyroligneous distillate. Distillate because this retort flask here has collected the vapors and condensed them. Pyro meaning fire, and ligneous derived from wood. So we have a pyroligneous distillate here, and we have the gaseous mixture there and the charcoal over there. Now, what I wanted to tell you next is, in this very simple, crude experiment, since this very crude experiment has been done, and people have found use not only for the charcoal, but for the gases and for the liquids as well, chemists have made great advances, and they have been able to do this type of experiment and actually analyze the products in much, much greater detail. And what I have set up here is an apparatus for doing precisely this. In this apparatus here, I have in this round bottom flask here, I have exactly the same material. I have a pile of sawdust. But this time, rather than crudely allowing the gas mixture, because it is actually a mixture of substances coming out there, in terms of states, this is a solid, this was a gas, and this is a liquid. In terms of chemistry, though, this is a mixture, and that too is a mixture. And I'll be explaining that because here, using this apparatus, we are actually going to separate some of the components of that mixture. And I'm going to invite, I have two assistants with me in order to carry out this experiment, because this will take about 15 to 20 minutes. And I will ask Andres to come on. Andres Tretiakov is the senior laboratory technician and chemical demonstrator at St. Paul's School in West London. And my son, Oscar, who is going to assist in the experiment today. Now, I'm going to ask Andres and Oscar to commence this experiment here, and I will explain the chemistry and the science of wood as they do so. Now, for this purpose, we're going to use quite a strong propane torch here, a propane torch with a significantly bigger flame, and it should generate a reasonable result. Now, on this occasion, rather than just allowing the vapors here to be separated into a liquid and a gas, we're going to pass the vapors, first of all, through a Dreschel bottle here, which I have. This is a type of bottle for collecting vapors and condensing them, and it's sitting in a beaker full of ice. What that will enable to happen is that the vapors will start cooling down and condensing much more efficiently than here. This is a Dreschel bottle which contains sodium hydroxide solution. Now, the sodium hydroxide solution here will chemically absorb one of the gases which is being produced in this process. And the gas which is being produced in this it's a mixture of gases, and carbon dioxide is one of them. I think we can start collecting, Oscar, probably, okay? Now, the reason why I'm going to be giving a little bit of direction is because this is not at all an easy experiment, and the mixture of gases, I'm telling you straight away, it's not one gas which comes off, but it's a mixture of gases, not too strongly, just a little bit gently. Don't collect all the gases, Oscar. I'm giving a commentary. There are about 30 gas jars will be collected. Oscar will only collect 5 of them. And the reason is we want to show you how the composition of the gas changes as the process of pyrolysis continues. Now, dear children, one word I wanted you to learn today is what's happening here. This experiment, or what we're doing here, breaking down a substance by the action of heat, is called pyrolysis. And it is a word which used to describe this process of breaking down wood into simpler substances. Now, one of the gases coming off is carbon dioxide. Some steam is produced as well, but in those jars will be collected a mixture of 3 main gases which are produced, which we're all burning here. And I'll tell you what those 3 main gases are. They are carbon monoxide, hydrogen, and methane. I will put this up on a screen for you later on, and I will demonstrate each of these gases individually. Now, while this reaction is taking place, I will tell you a little bit about what wood actually is made of. And we can consider wood from 2 directions. One from the point of chemistry, what chemicals is it made of? And I'm sure you'll agree that this is not one substance, it's a mixture of lots of substances which have been produced by nature. It's a mixture of substances, and they are essentially natural polymers, very, very large molecules. One of them is called cellulose. It's the same molecule that you find in cotton wool, in paper and wood, and indeed it is one of the main molecules that is found in all plants. Another group of molecules are called hemicelluloses, and the third type of molecule in wood are called lignins. Now, I will very briefly explain 3 types of molecule. Celluloses are carbohydrates, which are polysaccharides. They're made up of lots of sugar molecules, which are produced in the plant, and they join together to form the structure of the cells in the wood. Hemicellulose, and they're very organized. Cellulose is very strong in tension, and they're long, and they are arranged quite regularly in the structure of the wood. Hemicelluloses, as the name suggests, are much shorter molecules. They are composed of different types of sugars, and they're slightly more haphazardly arranged, but they are necessary, and they contribute to the structure of the wood. And the lignin is the main type of material which is only found in wood and not in other plants which don't contain the wood. The lignin is the woodiness of the plant. Now, lignin is a most fascinating mixture of substances, and the difference between lignin and the cellulose and the hemicelluloses is that lignin has lots of aromatic groups in it. It's a different type of chemistry. Lignin is strong in compression, and it gives wood that very, very hard, that relative hardness with which we associate wood. And I will be coming back to these terms because understanding what we have at the start will help us to understand, to identify and discuss the products which are made at the end. Now, how are we getting on, dear Andres? How many jars have we got so far? It's okay. Thank you very much indeed. So, I'll explain to you also what the substances are, a little bit about them, before we continue further. Oh, I know, while that's actually going on, I wanted just to tell you a little bit, because this will take another couple of minutes, a little bit about my own favorite woods. I have 2 woods which are my favorites. One of them is balsa wood, which is the wood out of which these models are made of. And the reason why I like it so much is because it is the lightest, it has the lowest density of all the woods in the whole world. The density of balsa wood is 0.3 grams per centimeter cubed. Now, because it has such a very, very low density, it is fantastic for making models with, etc. And I wanted to show you, by the way, I got a question which someone might come and tell me the answer to. Did you know, dear children, that there is a metal which exists, which has the same very low density as balsa wood? This is supremely light. You will not meet this metal on an everyday basis, but if anyone can come and tell me at the end of the lecture which metal has the same density as balsa wood, he will receive or she will receive a prize from me. The person, preferably someone of the younger age group, please. Now, may I return, although I suspect it might be a challenging question for non-specialists as well. Now, what I wanted to show you is just simply how my own interest is. I've got two models, as you can see here, made out of balsa wood. This, you see, is a boat made out of balsa. I made this when I was 8 years old in 1958, and I used to sell it. I used to I had a little outboard motor and a little celluloid window, and I used to sort of sail it in the paddling pool in Hammersmith Park, close to where I used to live. I regrettably sometimes hit the bottom, and then the hole, so I put some patches on it. But because I spent so much time making it, I could never bear the thought of throwing it away, and that's why I brought it here. Now, I used to make lots of model aeroplanes. Regrettably, they all crashed on their first or second flight. So it was a lot of time, etc. But one has survived. And I brought this to show you here. It's not in very good condition, but it is made of balsa wood. It's a control line. You sort of put it, or you have a motor, and you go like that, and it flies around on long things with a motor on it. Now, the only reason why I've still got this is, of course, because it's the only one which didn't crash. But the reason why it didn't crash, because it never flew. So that's why I actually couldn't get the engine to work. I was a disaster. Now, Oscar, would you be able, have you almost finished the jars? Oscar's actually just wanted to show you, dear children, it's such fun making these little bowls. They're very cheap, you can buy them. Oscar, could you just demonstrate that? You demonstrate this, I'll collect the last jar. Just give it a few throws. We must entertain ourselves, children. So this is a little bit of aerodynamics, a little bit of aeronautical. Did it fly? Has it flown? Oscar, thank you very much. Thank you, Andres. This is brilliant. I've now collected the last jar. Now, another one of my favorite woods. Please excuse me, do we have some tissue? Oh, yes, we do have. By the way, I have to tell you secretly, under here we have many useful things. So I've got tissue, we've got rubbish bins, all sorts of things. This really looks very, very beautiful, Andres. I think we have a fantastic result here. And as you see, once the heating has stopped, the products will start to cool down, and very shortly we'll be able to analyze. But I just wanted to tell you about another one of my favorite woods. And I'll tell you why. It is maple. I'll tell you why the maple is one of my favorite woods. Well, because first of all, it's because you can actually drink it. It's one of the few trees where you can get a product from the woody substance of the tree. And this is here maple syrup, and I'm sure you all enjoy maple syrup. But not only can you eat maple, but you can also make splendid musical instruments from them. And I would like to just demonstrate for you. I have a musical instrument because I love music, and I wanted just to show you such an example of playing a tune. Thank you very much, Oscar. This is a viola, and it's made of maple. So we have wood. We don't necessarily have to burn wood all the time. This is, by the way, a Slovakian melody. Now, you see, that's a very straightforward melody, you see. But the honest truth is, to a little sociology, my dear children, is that, of course, when people used to meet at campfires and bonfires and things to play. They used to meet in large groups, you see, and they used to talk and make food, etc. And music was not only made by just one person necessarily, but groups of people used to gather. And I just invited a few of my friends with maple instruments to come and play you a Romanian folk melody. So if we can just come on, where are they? We'll... So there we are, just a little music. Thank you very much to my friends, my Romanian friends. As you see, wood doesn't always have to be burnt. As you know, there are thousands of uses. And now let's rapidly return back to chemistry. Thank you very much, Oscar. Let's return to the chemistry. Thank you so much, dear Andres. Is absolutely wonderful. Now, what's happened, Andres? In the meantime, we've had a suck back. Not to worry. That's unfortunately, some water got sucked back. We got carried away with the music. And in fact, it's gone right back into the flask. Now, this, by the way, does show some very interesting principles of physics, dear children. And we continue to learn. When you heat gases, they expand, but when you allow them to cool, they contract. And what we've happened here is, as we took our eyes off the equipment, the water, as the flask cooled down, water got sucked back from here, into there, and into there. And I'm going to show you another experiment at the end, which shows you this exact phenomenon with some very, very nice color changes. But, so what we've done is we filled the flask. But not to worry, we have collected our gases here. We have also kept, just in case this happened today, I have a sample of what is known as the pyroligneous distillate here. And what I wanted to do is to explain to you a little bit about these substances which we have here. And I'm going to start off by telling you that the charcoal which I have here, which we have a small... Oscar, could you sprinkle some charcoal? This is the... sprinkled some charcoal into the flame. This is from a previous experiment, which I said we'd have kept supplies because we are ready for all sorts of circumstances. And the most important thing is not to have an accident, of course. And just sprinkle a little bit just to show. Can you see? That is just charcoal. Some more, a generous supply, dear Oscar. We don't want to be mean with our thing. Shows many sparks. That's much more like it. So this is just charcoal burning in air, you see. So what we're now seeing is that when wood is pyrolyzed, broken down into simpler substances, those long molecules of celluloses, hemicelluloses, and lignin are broken down into shorter molecules. They form a wide variety of substances. Now, dear Oscar, could we try and ignite these jars one at a time? Because we'll do the gas. No, actually, I'll tell you what, let's first of all do one thing here before we do the gases, and then just look at this pyroligneous wood distillate which we have here. And I wanted to show you that the pyroligneous wood distillate consists of two layers. I very much hope you can all see them. There's a sort of orangey layer, and at the bottom there is this thick, oily liquid which is sitting at the bottom there. Now, the oily layer is from the lignin part, which is the aromatic hydrocarbons, which don't mix with the aqueous layer, which contains obviously water, but three very important organic chemicals. And one of them is methanol. See these two flames burning here, dear children. These flames here, these are little spirit burners, but they have methyl alcohol, methanol, CH3OH, which was for many years called wood alcohol. And do you know why? because it was obtained from the pyrolysis of wood. So that's one of the things here. And another product, which I will demonstrate in a minute, is ethanoic acid, acetic acid, the acid found in vinegar, amazingly enough. And another one is acetone, propanone, which I have here, and I will show you that. I wanted to start off, though, by showing you, first of all, that this fluid, this liquid here, is acidic, that it turns certain natural products to certain colors. And with that aim in mind, I'm going to use an indicator which I have prepared here. Now, dear children, this is it is extract from red cabbage solution. And this, you see, there's a reason why I smelt it, because it smells rather nice like cabbage soup. You know, when I was cooking this yesterday, I thought to myself, what a shame. It would be so nice to eat this cabbage soup. But I thought, no, we shall show it to the children because it can demonstrate something very useful. So I'm going to pour some of my cabbage extract soup into there. And what I wanted to show, there it is, it's gone in. And I'm now going to add a tiny bit of my pyroligneous fluid to it here, dear children. And please notice any color change. And you see it's gone bright red. Now, not bright, but it's gone a sort of red. Now, the reason why it's done that is because inside here is, in fact, acetic acid, acid which is found in vinegar, ethanoic acid. But I also wanted to draw your attention to a most interesting fact. This cabbage indicator here is not my invention. It's not teachers. It is something that has been around for thousands of years. And one of the greatest scientists of all time who worked in this laboratory here, and who made the world's most fundamental inventions and gave talks here, was Michael Faraday. And I wanted to tell you, I am very, very, very lucky that I have got Michael Faraday's book called Chemical Manipulation. Now, this is a book especially written for students of chemistry, and this was published in 1842, and it's in beautiful condition. In here, you see, in this book here, Faraday described how to make red cabbage indicator, and that's what I wanted to tell you about it. And I actually have I wanted you to see a little fragment. I'm sure we'll be able to see this fragment very shortly. But while we're waiting for that fragment to arrive, I'm going to move on to the next text. Oh, let's see these gas jars burn. That's right. So I've told you about 3 liquids which are found in here. We've examined one property of this. This is a mixture containing, as you saw, an oily layer, and etc. And I'm going to now ask Oscar to ignite the jars one at a time. And allow me to tell you why. Because as the process of pyrolysis continues, so which one was first, Oscar? That one, okay. Now, we're not sure whether we'll be able to pull this off exactly, but what I wanted to tell you was that the first gas which is produced, because they come off in various sequences, is carbon monoxide, which burns with a blue flame. We may be able to get that result, depending on, it may not burn at all. That, you see, is air. That's fine, Oscar, not a problem. That shows you that when you heat substances, and carry on with the next one, Oscar, did you see that? Very good, Oscar. Now the next one, please. This should burn even more beautiful. And you see now, the flame is burning differently. Now that's almost pure carbon monoxide. However, as the pyrolysis proceeds, we start to give off a different type of gas, and the hydrocarbon, which may burn with a slightly yellow and smoky flame. Please watch carefully. You can see a little bit of smoke. Now, the last one should burn with the smokiest flame of all, and that will be almost pure methane. And there it is. That's it. Can you see that? Now, that graduation there shows you that the composition of the gas mixture changes as the process. Thank you very much, Oscar. Now, thank you very much. We've got some extra mats coming in. Very much appreciate for the burners. For the acetone. Thank you very much. Oscar, that's wonderful. Thank you so much indeed. Now, what I wanted to show you, dear children, you know, I like to do things in slightly larger numbers. And I wanted to show you a little bit about, I'd like to make more carbon monoxide, basically. And the reason is, for me, just watching those fleeting blue flames isn't quite enough. So I wanted to show you a far bigger blue flame with carbon monoxide, which I'm going to produce here. Just allow me to put that on there. Oscar, could I kindly ask you to remove the gas jars and just take them off? Thank you so much indeed. We are going to be continuing continuously moving things around in order that you can, thank you so much indeed, in order that you can all see slightly better. Yeah, then take these away at your leisure, dear sir. Take them away at your leisure. Thank you so much indeed. And what I wanted to show you next is how we can make, whoops-a-daisy, I just dropped a gas jar lid. It has not broken, so we're still very fortunate. Multitasking is the essence of today's lecture, as you can see. Now, well, I'm just trying to find a nice position to put this in. And do you know what? I think I'll do it over here. I'll tell you why. Because I want to exploit the splendid facilities that we have here and show you this experiment over here. Now, I'm going to make pure carbon monoxide for you. Now, carbon monoxide is a colorless, odorless gas. The chemical formula is CO, and it is intensely poisonous. It is the fact that it's poisonous is not the issue, because many poisonous gases you can smell and run away from them, but not so with carbon monoxide. Carbon monoxide kills by stealth. You can't see it and you can't smell it. And before you know it, you've lost everything. So I'm going to make some carbon monoxide now by pouring concentrated sulfuric acid onto sodium formate. You will notice a considerable amount of frothing, and then I will do my favorite thing, which is to set fire to it. And I want you to observe the beautiful flame. And I can reassure you that this flame is completely harmless. And you'll see very shortly some frothing. There it is. It's beginning to froth. As I add concentrated sulfuric acid, we replay, and there it is. Now that's deadly carbon monoxide coming off. And here it is, burning with the beautiful flame, you see. Now that incandescent blue flame, as carbon monoxide burns, it of course makes carbon dioxide, which is of course completely harmless. And as long as the frothing is continuing there. But you may like to know, so carbon monoxide, a deadly poison, but in this case it's of course entirely contained in it. We're burning it off to make carbon dioxide. And Andres will show you a very clever trick for making this completely harmless in just a few seconds. And what I wanted to tell you is that carbon monoxide, although it's a colorless, odorless gas, and it is commonly given off when things don't burn completely. Tiny amounts are produced when fuels burn, etc. But obviously they're controlled so as to. Let me just add a bit more sulfuric. I'm sorry, I just do like this. And it should froth up a little more. You know, it all depends. Let's give it a little stir around there. There we are. A nice, blue, beautiful flame, you see, etc. Now, carbon monoxide does undergo some very, very interesting chemical reactions. For instance, when I was at school, we used to learn to test for carbon monoxide, you use pallidus chloride paper. Pallidus chloride paper was white, and when you put it into carbon monoxide, it went black. It was essentially reduced to the metal palladium, which is a hugely interesting metal about which a great deal of research is being done at the moment. But another interesting thing about this gas carbon monoxide, it can actually combine with certain metals, to combine directly with metals to make what are called as carbonyls. And there are two particularly well known. Iron and nickel carbonyl are metals which if you pass carbon monoxide over iron powder or nickel powder at a high temperature, you'll get an oily liquid coming off, which is intensely toxic. But nevertheless, it has interest. These carbonyls have very interesting applications in purification of substances, etc. And I don't want to go into detail, but the honest truth is they give some very interesting examples of how chemical bonds exist between substances. Metals normally form ionic compounds with charges on their ions, but in the case of the carbonyls, the metal is bonded in a completely different way. We don't normally see liquids which contain metals as part of them, but carbon monoxide is a substance. Now, my dear sir, if I can ask you to extinguish that, what he's going to do essentially is to pour water into it. And as he pours water in, the flame will get bigger because the water displaces the carbon monoxide, and at the same time, it stops the reaction from happening. So by doing this, we have not only stopped the reaction, but we have also reduced, there is no danger of any carbon monoxide being, and at the same time, we had a little bit of extra flame produced, which was the most important. Now, the next thing I wanted to show you, see, is to turn to our liquid product. I wanted to start off by telling you that this pyroligneous distillate, which we have a small quantity of here, is not something which is useless. People have been talking using charcoal for a very, very long period of time, and I'll tell you about the charcoal in just a few seconds. But we're going to focus on these liquids, and people don't actually have to know the chemistry of it. Making charcoal is thousands of years old. Making this pyroligneous distillate is thousands of years old. And you don't have to know how it works in order to use it. But I am going to just tell you that one of the uses of the oily layer of this, or some of the uses, have been, for instance, in the past and still today as an antiseptic. The oily layer has been used to make leather waterproof. It is used, also has been used, and this is known, the Egyptians, when they used to embalm mummies, they used to use this pyroligneous tar, as it's called. It has amazing preserving qualities. And not only that, today I have here a bottle of shampoo. I have a bottle of shampoo, and believe it or not, this is wood tar shampoo, and it reeks of this stuff here, and it's still used, and it's still made today. So these ancient technologies still have some uses today in the modern world. But back to fires. And you know, of course, it's not surprising that most of the experiments I'm going to show you today involve fires. Why? Well, because when wood burns, bonfires is the topic. Well, obviously, everything associated that comes off from the wood will burn as well. And this is, therefore, now I'm moving on to the methanol is burning here. That's one of the three main products. Then we have the acetic acid, which is here, which turns this, the cabbage indicator red. And now I'm going to show you acetone. Today it's called propanone. It's a universally used solvent. It used to be used as nail varnish remover. Has a smell which I like, but you mustn't smell these things, children. Now, I'm looking for a 50 centimeter cube measuring cylinder there. Thank you very much. Andres is my friend, always on. Now, I wanted to show you how propanone burns. But, you know, just to burn a few drops would be a completely pointless exercise. I have made a little steel trough for you here. And now, where's the ether? Is the ether? Good. Oscar, you're going to get ready with some splints to show us the flashover effect, which I hope we'll be able to show. I'm not sure. It may, you know what, for this experiment, it may be useful to dim the lights. Once the flame is alight, though. Once the flame is alight. Oscar, there we are. And I will pour the ether in, and Oscar will then show you. But let's first of all just show this is 50 centimeters cube of acetone, otherwise known as propanone, and I'm pouring it into my steel trough. Now, I very much hope it's horizontal. Take your time, Oscar. Now, we're not in a hurry at all. No hurry at all. I'm just checking to see that we have, yes, it is level. Now, please watch carefully. A flame will spread down. Yes, take the lights down. Thank you. This is brilliant. Yes. Now, as you see, the propanone is burning. But children, this is nothing. We're just beginning. There's quite a bit of it there. Now, this is the interesting thing. Oscar, could you stand back to let some people see? Thank you very much. Now, as this propanone is burning, you see, and it's in a metal trough, that metal will get very, very hot indeed, obviously from the flame. Notice the yellow color of the flame. This is what we call incomplete combustion. Tiny bits of soot are produced. But as the trough gets hotter and hotter, so the propanone starts to boil. It gets very hot indeed, and therefore the flame gets bigger and bigger. And that's the only reason why I do this experiment, because I love flames. So as you see, the flame gets bigger and bigger, and then it will eventually, obviously, go out. Now, while that is getting bigger and bigger, allow me just to click onto, where's my, thank you very much, it's been repaired. Now, I'm sure you've all seen this. So this is Michael Faraday's description of how to make red cabbage indicator. And what I wanted to tell you, the greatest chemists in the world use this. It's very simple, and I've got some more experiments with the indicator to show you. Now, the next slide. You did see Michael Faraday. By the way, I wanted to tell you, photography was invented in 1822 by Nicéphore Niepce. He was a Frenchman. And it took the whole of Europe, the whole world by storm, photography. And Faraday loved photographs. It was state-of-the-art science, and he loved being photographed. And that's a portrait of him, which I particularly like, and that's why I wanted to show it to you. So now that we move on, dear children, this is a little bit of theory for you. And this is main fractions. This is taken from a modern textbook on the chemistry of wood, and it shows you the main fractions obtained from wood pyrolysis. Now, pyrolysis is this new word which I wanted you to learn. But we'll come back. This has almost burnt itself out. We'll come back to that in a second, and you can practice and learn that all off by heart, children. It's not too much, and I'll explain to you once you've learned it what it is that you've actually learned. There's some fairly tricky words and pronunciation-wise. Now, what I wanted to show you next is a very interesting effect. I'm not sure whether it will work here because there's a little bit of a draft here. For obvious reasons, we need good ventilation here. But what I wanted to show, it's gone out. I'm now going to pour in 10 centimeters cube of ether. Now, ether is a stunningly volatile liquid, and it's similar. It's very similar to the product, and that will vaporize. Little Oscar, have you got your flame ready? Hang around, let me pour it in. Can you see it's turned to a vapor? It's all now, hello! And that's what I wanted to show you. Wasn't that amazing? He got there before I did. Oscar, that was very well done. So that was a flashover. So, now, the purpose of showing you this, dear children, the purpose of showing you this is really a bit of health and safety. The honest truth is, when you handle flammable liquids, and this is present in industry everywhere, you have to be phenomenally aware of the way in which they can catch fire. And I'm sure you'll agree, in this controlled experiment, it's perfectly okay, slightly out of control, but nevertheless, it was perfectly okay, but it's very easy to have industrial accidents, etc. And the substance that we use on an everyday basis, which will conform with this type of behavior, of course, is petrol, which we use in motor cars every day. Unbelievably dangerous. And when you handle, the golden rule is, whenever you handle flammable liquids, make sure that all flammables are out of the way. You notice here, I'd removed all the bottles. There is no flammable anywhere, and all the flammables are illuminated. And I also used a small amount. So I knew I was covered, and in this particular experiment. Now, let's just return back to what you've learned in the meantime. So we have wood. The important thing is wood makes gases, and there they are. Don't worry about the formulae too much. I think water is H2O. Carbon dioxide is the one that we collected in here, you see. Then that doesn't burn. That's why we isolated it. Methane is the hydrocarbon, and carbon monoxide is the blue one, and hydrogen, which I'm going to show you at the end. Now, that's there. Now, the distillates and the tars, they've put up a bunch of compounds there, and I wanted to tell you that the top three are the ones I've demonstrated for you today. CH3COH is ethanoic acid, CH3OH is methyl alcohol, otherwise known as wood alcohol, and the third one is acetone, CH32CO. All the others are present in the oily substance. Now, the last thing I wanted to come on is to charcoal. Can we have the next slide, please? Can we have, oh, sorry, thank you very much, silly. And just in case you found that rather easy to learn, here is a complete list. So just in case, children, you think you're getting on top of the subject, learn this off by heart for Monday morning's test on the products of the pyrolysis of wood. And there are, I tell you what, I haven't memorized them, I just counted them. There are 60 of them. Quite a large list. Now, I have actually, because this is a stunning list, I'm sure you'll agree, that is all produced, and when you burn wood, you're burning all of that lot at once. And what I wanted to say is that I put circles around. So the orange, those are what we call carboxylic acids. The ones in yellow are alcohols. The ones in light blue are the aldehydes. Dark blue are the ketones, and the dark blue and the light blue are the carbonyl compounds. The next ones are phenols, and the purple ones are phenols, basically derivatives from benzene, and they're aromatics. And then we have nitrogen-containing compounds based on ammonia. And then we have some aromatic ethers, and finally some aromatic hydrocarbons. So by gum, what what a complex mixture is indeed. So when you're burning wood, dear children, you're burning all of that lot. I just wanted to tell you another thing about these aromatic compounds. These aromatic compounds, they're called aromatic. Why? Normally, carbon atoms, when they join together, they make long chains. That's the sort of simple compounds that we have, that we're primarily made of. Cellulose and hemicellulose and all the other ones apart from the aromatics. However, carbon is also able to form a most unusual group of compounds which perplexed scientists for many, many years, which are based on the chemistry of benzene. And they form hexagons, like beehives have, bees make their hexagonal wax cells they live in. In this particular case, the carbon atoms form rings of 6 carbon atoms, and the basis for those is benzene. Now, believe it or not, another thing, Michael Faraday, precisely in this building in 1825, discovered benzene. And that is another one of the great achievements of this remarkable man, of profound humility. And he made so many discoveries in the branches of organic chemistry, inorganic chemistry, not to mention electromagnetism and all the rest of it. And to bear in mind that he left school at the age of 13 to train as a bookbinder. But more on that on another occasion. And you should also know, dear children, that this year we are celebrating, or we are commemorating, the 150th anniversary of Michael Faraday's death. He died in 1867. He was slightly over, he was born in 1891, so that makes him 76, I think, and etc. The fact is, he's buried at Highgate Cemetery, which is North London here, and he was so humble that on his grave it simply says Michael Faraday, 1791 to 1867. Quite remarkable indeed. But this year is indeed the 150th anniversary, and please remember, one of the greatest scientists of all time. Now, are we ready for the next slide? Yes! This is a comment, you see, when chemists were analyzing all these substances, because the 19th century was a time when analytical techniques developed and separation techniques. The separation technique of fractional distillation developed, and the analytical techniques of chemical analysis, gravimetric analysis developed, ideas of atoms, atomic weights. Friedrich Wohler, who was one of the great chemists working with Justus Liebig in the early sort of third and 19th century, when he discovered all these chemicals and started analyzing and making these lists, he said to me that organic chemistry appears to me like a primeval forest of the tropics, full of the most remarkable things. And those most remarkable things, dear children, are all these compounds, that huge list over there. Now, let's see what the next slide says. And there it is, dear children. I have especially for you prepared this little thing. On the left, we have the chemicals, the types of chemical that you find in wood. And cellulose, as I've said, made up of long chains of sugars. And hemicellulose are shorter chains with a variety of sugars. And lignin is the one which gives rise to the oily, the aromatic compounds. Now, how do those chemicals arise? Where does this happen? In the wood. What is wood from a biological point of view? Well, wood is basically dead xylem. The bulk of the wood itself is dead. Inside, this wood is dead in the thing. The only part of a wood when a tree is growing, the only part of a tree that's alive is the outside part of the tree, which is the bark and the layers under it. And below the bark, you have the phloem, which is part of the wood which carries liquids which are made which are basically water containing sugars and things which come from the leaves. You see, the wood, dear children, a tree when it grows exchanges or takes in and throws out chemicals through the top and through the bottom. Through the bottom, it has the roots, which take up water and nutrients from the soil, and those flow up the tree through what is called the xylem, whereas the leaves, where they are green, etc., and they, by the process of photosynthesis, they convert water and carbon dioxide, which are in the atmosphere, very simple substances indeed, and by complex processes, they convert them into sugars and then into larger molecules such as starches, celluloses, and so forth. But cellulose specifically is the main thing in wood, you see, and wood is that thing. And there is a thin layer in between the phloem and the xylem, and that's called the cambium. The cambium is the part where these types of two separate types of transporters of liquid are actually generated and where they grow. And this is all just under the bark. Inside, the bulk of the tree is dead. By the way, the word xylem is actually derived from a Greek word meaning obviously wood, and the word phloem is derived from the Greek word meaning bark. So we have these words of various languages. Now, that you see, I just wanted to tell you, I had a very interesting experience this summer, specifically on July the 26th. There was a very, very heavy rainstorm in our back garden, and a plum tree which I had, which was beginning to have lots of plums, unfortunately split in half. The stem split in half, you see, and it is, and I was very, very disappointed. And I photographed, and I said to myself, is it possible to repair it? Because we're going to lose all our plums this year, etc. So what I did was I tied the two halves in the next strip here. I tied the two halves together, and this is the reason why I wanted to show you, is because when the true halves, they won't grow together, by the way. They won't grow together, but by tying them together, you're giving it mechanical strength so that the two halves continue to absorb through the phloem and the xylem all the nutrients which they produce within the wood, and they can grow independently even though they're joined together. And what you have oozing out in between, this is the important bit, it's that sap which is coming out. Now, it's from that sap on the maple tree that we can make maple syrup. Now, that sap is it comes from the phloem, and it contains the sugars which have been formed ultimately from the leaves at the top, and that sap, and I have the next slide to show you, and please watch carefully. Oh, that's our plum crop. We had an amazing plum crop thanks to the fact that I got the trees. But on the right-hand side, can you see that little snail? It's having its lunch. It's eating the sap from the plum tree, you see. And that's a very, very remarkable thing, because you see, that sugary sap is food for others, not only human beings. But I was very, very lucky to be able to capture that image. Now, the next word, please, is pyrolysis. And this I'm going to leave up, because this is, if you're not very clever, children, don't worry if you're not. And if you haven't learned all those lists off by heart, one word: pyrolysis. Pyrolysis is derived from two ancient Greek words meaning fire and breaking down. So that's one word, please remember. And now I'm going to come on to the final product of the combustion of wood, which is, of course, charcoal, which is left at the end. And Oscar has already shown you how charcoal burns. And charcoal is an almost pure form of the element carbon. It is the soot which is produced when sooty flames burn. And furthermore, this carbon is the source of a remarkable number of uses throughout the history of the human race. And I just wanted to show, thank you very much. And also we can get rid of the aeroplanes, dear sir. That would be much appreciated. And I just wanted to show you a few things about charcoal. Now, charcoal is an impure, we finish with that. Thank you very much for tidying up, gentlemen. Charcoal is an impure form of the element carbon. Charcoals, they vary. The proportion of carbon in charcoal can be anything from 90 to 99%. But no matter how long you roast that wood for, pyrolyze it for, you will never make 100% pure charcoal. The thing about charcoal, it has a very, very porous structure, and that gives it a large number of uses. But before I talk about charcoal and different forms of carbon, I wanted to say that there are two allotropes or forms of charcoal, the element carbon, which are not called charcoal, but which are here. And one of them is here, and that is a piece of graphite. That's a crystalline form here. And I have here one other form, and you see here, these are pure diamonds. It was a source of great challenge for scientists to understand, and I'm going to see if you can I hope you can see, these are real diamonds made out of pure carbon. They are very, very valuable. They're rather small, I'm afraid, but I very much hope you can see them glittering, because it's that property of carbon, of diamonds, which makes them so very, very special. They have a remarkable refractive index that makes them useful as precious stones. Now, do you know what? For many, many years, scientists could not believe that this and this are made of exactly the same atoms, carbon atoms, which are found in charcoal. Now, would you believe that experiments were conducted by scientists, initially in Florence in Italy, but even Michael Faraday, when he went on a tour of Europe with Humphrey Davy between 1813 and 1850 in Florence, because they were still doubting. They said, how can this be the same as this, the most precious stone in the universe? And they did it by burning. And if you burn some graphite, and if you burn diamond, a very expensive experiment indeed, then equal masses of graphite and diamond burn to give the same mass of carbon dioxide as the only product. Now, Faraday actually described that burning process, because they showed it to him in Florence, and he described the brilliant crimson flame that diamond made. Now, charcoal, of course, is also useful for drawing, as a drawing thing. So I'm just going to use a piece of charcoal just to draw you my experiment number one. And it has been, this is not art, this is science, and I'm just going to show how we can represent the flask which I did the distillation in, the retort flask like this, you see, and using a piece of charcoal, the teacher, you see, can then illustrate this to the students, and we have a ground glass stopper like this, and then we can put the stopper in like that, and then we have our drops of distillate coming off here, you see, and this is our pyroligneous distillate. My word, it's been a lesson in many new words today, and I very much hope, there it is. And here we have, for instance, the flame, which is roasting it. Here we have the bits of wood and the charcoal like that here. And then we put a nice label on it, like this, retort flask here. And we have a nice arrow pointing to it. Et voila. And then we can even color it in. You see, I do love colors. And then we can just shade in with a little bit of blue to show the blue cone of unburnt gas here. Then a little bit of purple there, you see, and then we can shade in the smoke which was coming off, which had a sort of a dark, thank you very much, dear Andres, and then we have a colored, the dark color here, that was the color of the thing, and so forth. And you see, I am very quickly making for you a very simple sketch of an experiment which I have done, but using one of the products of one of the experiments, and that is something, you see, there, while we can have our pyroligneous liquid there with the oily droplets of the tarry residues there. Thank you very much. I'm not going to sign it. That would be very silly, but please take it away, dear sir. So there we are, another use of charcoal. Now, of course, do you know what? Charcoal is also available in shops as activated charcoal. You can buy it, the chemist buys it. And activated charcoal, this is used for a tooth whitening powder, you see. And you brush your teeth with it, and it apparently makes them white. But I thought they were white in any case, but it doesn't matter. People buy all sorts of things with the hope of improving themselves. And I just wanted to show you that we have here some activated, charcoal is used in water purification, has a huge internal surface area, and it has the remarkable property of being able to adhere to molecules and form loose bonds. Now, as I pour this is activated charcoal, which has been heated to a very high temperature to outgas it. I'm pouring my cabbage solution, and hopefully it will come through with no color at all. So this is now using activated charcoal to decolorize cabbage solution. Now, it may take a little while to come through, It may take a little while to come through because it has to absorb itself onto the thing. And my dear Andres, I'm going to ask you to bring on the gunpowder box now. You see, I wanted to show you my personal favorite application of charcoal, which is, of course, to make gunpowder. And I hope you're not too surprised by that. Gunpowder, of course, was invented, was discovered, or we know the Chinese were the first people to use gunpowder. And I'm going to show you today a little bit, a very quick experiment. Now, Andres, if you put that, that's brilliant, on the floor. I am going to very quickly instruct you. Now, you see, it's coming through absolutely colorless. This is a wonderful demonstration. This is a wonderful demonstration, again, of charcoal in action. It is taken out, and the reason is that all the dyes in the cabbage, in the natural cabbage, and also the smells have been adsorbed. By the way, the chemical word we use is adsorption. That means that the molecules in here, the tiny particles of cabbage and the smell, they have been completely adsorbed onto the carbon by forming loose molecular links, you see. Intermolecular forces are strong, and they have remained on the charcoal, which is remarkable indeed. Now, dear Andres, I'm going to start off. No, we start off by showing the three. Please excuse me for turning my back. We have had not very much time, but here we are. The gunpowder was discovered by Chinese over 1,000 years ago. 1,000, some people debate. How did they discover it? That is a remarkable, remarkable story in itself, which I don't want to go into detail. But the honest truth is by intuition. At the end of the day, we humans are terribly intelligent. Doesn't matter when we live or what we did, but we can work out lots of things for ourselves. And intuition is one of the ways in which science has proceeded over the ages. I'm slowly moving this stuff out simply because I want, my dear Andres, would it be possible actually to take this away? I've decided to change my policy on this. Thank you so much indeed. And simply because then we can have more space. Oscar, could you kindly take this bowl away? That would be most kind indeed. Thank you very much. We're creating more space, and I still have plenty to show. Actually, we're not that plenty, but enough. Now, the three ingredients of gunpowder are charcoal, which is in here, which are potassium nitrate or niter here, and sulfur, which is there. And what I wanted to tell you is that you can use charcoal. How did the Chinese discover it? What is it? Sulfur, I wanted to tell you, is a naturally occurring mineral. Occurs in many parts of the world, and especially in volcanic regions, but deep underground as well. Huge amounts of sulfur are extracted by mining, by some, we call it the Frasch process, but there are other techniques as well. We get it out of the ground. It comes out as the pure element, sulfur, quite remarkable. You cannot break sulfur into simpler substances. It is simply an element. Charcoal, mainly carbon, as I told you, and produced when bonfires burn, as we've just seen earlier today. But potassium nitrate's the clever one. And what happens is it's formed naturally in certain soils. The Chinese would undoubtedly have observed this, the fact that the things... Oh, and here we have, this is, thank you so much. I have especially prepared for you, dear children. This is a collection. These are potassium nitrate crystals. And I have grown them for you in this beaker. They are very beautiful indeed. And you are most welcome to come and look at them. And the honest truth is, in many hot countries, such as in India and in Southeast Asia, these crystals grow naturally out of farmyard soils. And where they grew and where there were embers of fires burning, those fires burnt much more brightly. And those were... Now, what I'm going to show you is what the Chinese learned. They learned some examples of these gunpowder in action. Now, as we're going first, I wanted to tell you first of all that the gunpowder mixture, which the Chinese invented, and we're looking at, let's say 1,000 years ago, contains 75% by mass of potassium nitrate, 15% by mass of carbon, charcoal, and 10% by mass of sulfur. And that was, those ratios, which sound like beautifully elegant numbers, were established purely by empirical means. There was no chemistry. You can't write a chemical equation. Today, chemists have not bettered the composition of the ancient Chinese had learned. And as I repeat, this is pure through sheer intelligence and intuition. Now here I have a mixture of those three, which is just to show you how it burns. If you do this as an experiment at home or at schools, and this is not particularly dangerous, you'll be very disappointed with the outcome, because this is how a mixture of these three powders burns on its own. And I have to warn you, this is not desperately spectacular. It will happen, don't worry, there it goes. Hardly gunpowder going bang, isn't it? It's not going to make you jump out of your seats, is it? Now, please observe carefully. Please observe carefully. Can you see these little blotches here? That was very slow burning. These little blotches, that's basically unused potassium nitrate, the bits of black unused charcoal. Simply the mixture isn't good enough to enable a rapid combustion. However, what the Chinese then understood, they then, using the technology of flour mills, etc., they thought, wouldn't it be good if we powdered them into a much, much finer powder? And then, when they made a much, much finer powder, they ended up with something like this. Now, this is, by the way, they called it serpentine powder. This is coarse serpentine powder, and this here is milled serpentine powder. This has been ground, this has been milled in a ball mill with lead balls crushing it up, making it into a very, very fine powder indeed for several hours, for 8 hours. Now, watch how this burns. It's quite a bit different. It's faster, and secondly, can you see that there are no residues of yellow? Now, not only that, they then used bread-making technology, in other words, dough, mixing with water, etc., and baking it, but not in the case of this. They took the milled powder, they then added to it small amounts of water and alcohol, and then they put it through a sieve, and they allowed it to dry, and they ended up with something like this. Now, this is what we call corned powder. Now, this burns quite a bit more dramatically still. So please watch carefully, because this will hopefully be quite a bit faster. I'm just going to wait. It takes a little while. Sometimes I may have to be daring and shove it. Whoa, just look at that. Now, that was, no, here. Now, please, look at that beautiful smoke ring that we've got. Wonderful, wonderful. Now that you say, can that make something go bang? Oh, yes, it could, because this is definitely gunpowder. And that you see, the result of human ingenuity. That doesn't require a great deal of theory, and we not have improved. Now, when the Chinese made this, they said, brilliant, let's now use this for some purposes. Thank you very much. And I'm going to show you very quickly how to make a simple pyrotechnic device using it. My dear Andrea, I just wanted to, Andres, I'm going to very quickly wipe down the bench. So please excuse me. I'll just quickly wipe it down. We must have dry circumstances. Thank you very much indeed. Thank you very much indeed. This is wonderful. And I'm just going to quickly make for you a Chinese firecracker. Now, we have 2 sheets of A4 paper for this. Now, I need my tape and the scissors. Brilliant. Thank you very much indeed. And the way we do this is as well. We roll up, first of all, we have to make, and you know the Chinese, they always interpreted, or lots of things they used to interpret in terms of dragons and things. And they call this gunpowder the fire dragon, or, you know, so things along the, very imaginative. And that in the course of human culture, we people are we like having picturesque ideas or analogies. Thank you, that's when. Now, excuse me, if we cut this off, dear Andres. Okay, we cut this off. I will now, right up there, and I will now wrap this tape around. Now, what we're going to do now, we're going to now wrap this up like this, and to make a tube. I'll tell you, give me the roll. Just give me the roll. Let me wrap it up from the roll, because it's easy. If you just cut that off there. Just cut that off there. Thank you so much. And the way we do it is this. It gives you and what we're doing, we're strengthening it, you see. We're now making a prison for the fire dragon. That's, you know, a sort of way you can look at it in a picturesque manner. And we're making it stronger simply by wrapping this around here. And there we are, like that. And now we trim it off with a pair of scissors. Thank you so much. Take care not to let the tape go there. Thank you so much indeed. Now, what we're doing now, we now have a tube. No one will deny that we have a tube. And now what I'm going to do is to seal the tube off at the end, because we are going to put some gunpowder in, obviously, or some black powder. The way we do that, we cut off the end like that, and then we bend the end like this, and then we put more tape on. So now, thank you very much indeed, we wrap more tape around it like this. And basically, the more tape you wrap, the stronger it is, the louder will be the noise when the fire dragon escapes. So we have this. Again, thank you very much, dear Andres. Now, what I'm going to do, I'm now going to put in some of my powder. Some of my powder, which I have here. And for this purpose, I've got a small jar, which is probably labeled black powder, and a small spatula, dear Andres. A small spatula and a small jar. They'll probably be labeled black powder fast or something along those lines. Is that the one? Yes, sorry. I have smaller containers, beer, children, and have we got a small spatula with a small end on? You may not have an... That's the one. A whole handful, every tool at mine. Thank you so much indeed. Now, we put approximately 5 or 6 spatula measures in here. I'll do it carefully so you can all see what I'm doing. 1, 2, 3, 4, 5, 6, and 1 for luck, 7. There we are. Et voila. The more the merrier. Yes. So there we are. So here we go. Now then, you're down there. And now what we now do, we use our ramrod here to test to see whether it's all gone and to ram it down. So we can now test to see it's down to approximately there. What we now do is we cut the end off here, and then we put a fuse in. We put a fuse in with which we are going to set free our fire dragon inside. Thank you, this in here. And thank you very much, Andres. We now put it like that. So that's now going inside there. And then we bend it over. We bend it over like this, to make a solid, to make an absolutely enclosed cage. So if you excuse me, I'm bending it over and now going to put lots of tape on it to give it, to make it very, very strong, to bind it inside like this. So there we are. I'm just binding it up. Now could I have my banger cage, please? My dear boy, thank you very much. Now, at this stage, we are now ready to go. And I wanted to tell you what this, you see, I'm going to set this on fire. Now, if I were to put it on my hand, you see, like that, you will all agree that wouldn't be a very bright move, okay? Because the reason is, it might make a loud bang, it might rip a hole in my hand. So what we do is, we're going to, it's called a firecracker, I like to call it a fire dragon, which is going to be released. We put it in a cage. This is what I call a banger cage or a firecracker cage, and it's to protect me, obviously, from the effects of this. And this is steel, so there's no way. Now, there is a shelf in there, which you can see, and there are 2 ends which have got holes in them. And that is to allow any product to come off. Now, do we have some safety goggles? And I'll ask Oscar to do the ignition. And thank you very much indeed, Andres. Oscar, safety. Thank you very much indeed. There is no real danger. Andres will be well out of the way. Now, the firing range... Oh, we have another pair of safety goggles there, Andres. We have another pair. Let's all wear safety goggles. Now, the firing range is here to there, okay? Because the only way it can escape is from there to there. Oscar, I will ask you to light the fuse, and I will then put the end on, okay? So, there's the fuse. If you can light the fuse, I'll put the end on. I'll hold this. This doesn't always work, but it may make a little bit of bang, a little bit of a spark, okay? So, that's... please, let's have the fuse on. Now move away, Oscar. I'm out of range. So there it is. Shortly, hopefully, our fire dragon will be released from his cage with an almighty bang. I'm not sure. Ah! We did it. So there we are. Blast wave through the thing. Oh, I'm sorry about that. Now, Oscar, some rubbish here. That's rubbish. Right. Now, we have now come to the end of the topic which is concerned with the products of the pyrolysis of wood. And so when you're burning wood, you burn all these products. But I now want to say what happens when you burn the wood. Burning is one thing. Pyrolysis gives you all these products here, but what actually are the final products when wood is burnt? When you've burnt the charcoal, when you've burnt all your pyroligneous fluid, when you've burnt your hydrogen, your methane, and your carbon monoxide? The answer is this. There are 2 main products, and they escape into the air. They are called carbon dioxide and water vapor. From all that huge mixture, carbon dioxide and water vapor are produced when wood burns. And what is most interesting, those are the two ingredients from which wood was made in the first place, which is quite remarkable. This is the cycle of nature. Now I wanted to focus on the one product, solid product, which gets left behind. I've told you that carbon dioxide and water vapor are the two main products which go into the air. But left behind, we have a product which I have here, which no one ever draws any attention to. But here it is simply wood ash. It is the ash which is produced from the burning of the wood. And believe it or not, this too has had a huge role in the history of mankind. No, we humans, we don't waste anything at all in any process. Dear Andres, could I ask you to do me a favor and take away our beautiful flask here, which has become full. Thank you so much. Just with a tripod with everything. Thank you. Watch out. That's it. I will just mop down the tiny spillage, and then I wanted to show you something about the properties of wood ash. And I'm going to start off by pouring my cabbage juice through the wood ash. So I'm going to I'm going to, if you don't mind, move this into the center phase now. Into the center. Thank you very much, Oscar. That's much appreciated. Now, I'm going to now move these three flasks on the beautiful sheet of white paper into center stage. The reason is I wanted to show you now what is in here. You see the cabbage water has been totally decolorized by our activated charcoal. I'm now going to take, this is ash from a wood fire in my back garden, and I put it through a sieve, just a kitchen, a kitchen strainer, a tea strainer, a big tea strainer or a metal sieve, just to get rid of some of the larger bits. There is my wood ash going on, and let's see what wood ash is actually made of. This is the very interesting thing, because there are many very useful substances. This is what we call the incombustible part of wood, the part of the wood that doesn't burn. It's the bit that gets left behind at the end. Now, if I now pour through this my cabbage juice, please watch what happens. I'm going to very, very gently pour the cabbage on, and you'll notice there's a little bit of dust going up, etc. And very shortly, the cabbage will start coming through. And as the cabbage starts coming through, you'll notice, hopefully, a very, very significant change in color. It takes a little while to come through. What I wanted to tell you is it's going to come through. Let's just wait. It's almost there, because this has played a most important role in the history. And I'll tell you what, this ash has been used in soap making. Thousands of years ago, even in ancient Egypt, people were already we're already aware of the most important ingredients that can be used in this wood ash to make soap. And for that reason, the liquid which you can see coming through now, dear children, has a different color. It is coming through yellow. And the reason why it comes through yellow is because in this ash which I have, there are two very important compounds containing two different metals. And one of them is called potassium carbonate. And the potassium carbonate causes the water to be alkaline by a process called alkali hydrolysis. Please don't worry if you don't understand, but seeing is believing. And you will all agree that this is not red, and it's not colorless, it's coming through yellow. And the reason why it's coming through yellow is because the wood ash is reacting with the water to release potassium carbonate into solution, which is soluble in water, and to make that potassium carbonate into a solution. And when potassium carbonate dissolves, it undergoes the process of alkaline hydrolysis, making an alkaline result, which is the yellow color that you see there. And this was used as lye, L-Y-E, for soap making, boiling up a concentrated solution of potassium carbonate with natural oils oils, with plant oils, vegetable oils, etc., used to use beautiful soaps. And perfumed soaps were available, have been available by humans for thousands upon thousands of years. Now let's do another experiment. To see what else is present. And what I'm going to do, I have got some wood ash. I'm putting ash inside here. And I'm going to add to it a few drops of hydrochloric acid. Now, please watch carefully. I'm going to put some lime water, which is a saturated solution of calcium hydroxide. Now, for your information, children, this is very commonly used for testing for carbon dioxide. It's a standard chemical test, but I very much hope I can show you this working, because it does show, what it does show is that, thank you very much. Now, Andres, if you can put the acid in, give it a generous squirt, and we'll show that it'll froth. Nice and easy, there's no hurry. Now, can you see it frothing, dear children? Can you see it frothing? Now, it's frothing because it's giving off the gas which we call carbon dioxide. Please watch carefully as my lime water, as it bubbles, it starts to turn milky. And the reason why it's turning milky, because wood ash is in fact primarily a mixture of calcium carbonate and potassium carbonate. And why is that? Well, because wood requires the two mineral metals, potassium and calcium, for its well-being. It enables the gases, it enables the wood to function, its sensitivity to light and heat is increased, etc. Now, those two metals which are present in wood, I wanted actually to tell you a little bit about them. The reason is they were both discovered yet again in this building. But not by Michael Faraday, by Michael Faraday's mentor, who was Humphrey Davy. Humphrey Davy was an extraordinarily flamboyant character. He used to give amazing lectures. In fact, the reason why Albemarle Street became the first one-way street in London, because Humphrey Davy was so amazingly popular. People used to fly. He was an amazing character. This, by the way, is just to show you the topic that we're on. I hope you've seen. It's not too difficult to understand. Carbon dioxide as a gas, water as a liquid, and ash as a solid there. That's Sir Humphrey Davy. He was one of the first directors of the Royal Institution here, and he made remarkable discoveries precisely in these rooms. He was first who discovered potassium in 1807 by electrolysis and calcium in 1808 by electrolysis. And we are going to demonstrate each of these metals to you reacting with water. Oh, whoops, a daisy, I'm not sure. That's Humphrey Davy there. That's him. That's a caricature. He was such a character. He used to do experiments with gases, and gases were at that time very fashionable, and that's Humphrey Davy holding the bellows there, etc. This is a very well-known cartoon published in 1801. That's for our next topic. Now, we are now going to, therefore, to demonstrate sodium. Now, for this demonstration, I'm going to ask for the lights to be turned off, please. Well, not off or reduced. Andres is now going to add a few pieces of potassium to the water. There's water in there. Now, this reaction only lasts about 5 seconds, so it's a very short reaction indeed. And if we could turn off the lights, please, this will be very useful, because you will see a beautiful lilac flame in there for a short while. This precise experiment used to be demonstrated by Michael Faraday here in the 1840s with potassium, which was then a newly discovered metal. Please, sir. And that's potassium reacting with water there. You saw a little bit of a lilac flame. It catches fire. By gum, it's dangerous and it splatters. Now, if we come back to that in a second, I will now show you calcium reacting with water, and let's do that over here. We can do that. Actually, let's do it over there. So I will now show you calcium. Now, calcium reacts with water, but it is much less dangerous. And what we're going to do here, we're going to pour in some pieces of calcium, and I'm going to show you what's going to happen. Here goes now. This is water, and this is calcium. Pour in a few lumps, and it starts to fizz. very shortly it'll start to fizz, and it gives off the gas which is called hydrogen in very, very large amounts. And there it is, and we can set fire. And as you see, if we can have the lights down, you see a beautiful brick red flame. And that brick red flame is being caused by hydrogen, which is generated from calcium as it reacts with the water. And you can have no doubt about that was a very large amount of hydrogen coming off. Now, the next thing I wanted to tell you, this will continue to fizz, is that in each of these cases, can you see the product of the reaction here is a clear liquid. It's simply water, and it's colorless. It has no color. Whereas here, the calcium has made a milky liquid. Now that milkiness is caused by calcium hydroxide, which is not soluble in water. Potassium is an alkali metal, fully soluble, but calcium hydroxide is an alkaline earth element. Calcium is an alkaline earth. On each occasion, we have a solution which is strongly alkaline. So as I pour this in here, the cabbage juice should go a yellow color, and we swirl it around. Hopefully it'll go, yes, it's going, it's not fully yellow, not enough potassium. This one should go much more yellow. And then we just pour the whole lot in. And you can see there. So once again, the alkalinity. Now our next experiment is with this is your speciality. This is the yellow powder. It doesn't matter. Yellow powder, yellow powder, yellow powder. Now this, by the way, this is a very unusual experiment. This is an experiment which I call the flying spoon experiment. Now I do have to warn you, the bang in this is very, very substantial. And what we have in here is not gunpowder, which contains a mixture of potassium nitrate, charcoal, and sulfur, but is in fact potassium carbonate, etc. And what we happen is we have two spoons here. What we have is one spoon here and one spoon there. Now, while that is happening, we're going to lead us on to the next topic, because this makes a very loud bang, and this is not gunpowder, but yellow powder. Gunpowder is called black powder here. This is going to make a very loud bang, and the spoons will go shooting up into the air. And that leads us into the next topic, which is bangs. I'm continuing, because I'm rushing on to finish now. We now have Theophrastus Bombastus Aureolus Bombastus von Hohenheim was the first person who had a theory about the loudest bangs that we ever heard, which were gunpowder. Which were thunder. Thunder and lightning used to terrify people. Now, this is going to be very, very loud bangs indeed, and the spoons will go flying, so please be careful. Now, the fact is that he put forward the theory that thunder was caused by aerial gunpowder. And we have gunpowder before, but in the air. That turned out, now this, please continue, because when they melt, the bang is very loud indeed. It's going to be an ear-rendering, deafening, and it's an unbelievable reaction. When they melt, that'll be ready to go. I'll carry on talking. That, his theory of an aerial gunpowder, because he thought it was gunpowder exploding in the skies, gave rise to the Polish alchemist's theory of an aerial niter. He thought it was niter that had something about it in the air which made things burn better and breathe better. He published this theory in 1604. It was the most widely read theory, alchemical theory, for 200 years nearly. 56 editions in 6 languages was published, Sendivogius's work. And that's the sort of stuff he wrote. Just a couple of quotes.
Cover your ears.
Man was created by the earth. And we're ready to go, are we? Please cover your ears. This will be a very, very loud bang. I'm continuing to talk because I'm too terrified to do anything less. Now, for there is in the air a secret food of life, which in the night we call dew, and by the day rarefied what's invisible could use is better than the whole earth. It is the water of our dew, out of which nothing is, the saltpeter of the philosophers, by which all things are grown. That's one. And there's our flying spoon. And the second one about to go now. And the second one about to go. Now, it is saltpeter which is making these explosions. Now, dear children, although Paracelsus and Sendivogius eventually led to the discovery of oxygen, we now know that thunder and lightning are actually caused by discharge of static electricity. I have here a Wimshurst machine, which I wanted to show. So there it is, and I'm sure you'll agree. Now, I'm going to quickly twiddle the knobs here. Twiddle them. Now, as you see, can you watch? This is what makes thunder. It is an electric spark going off like this, an electric spark going off like this, and that electric spark is the spark which causes a huge expansion of the air and which causes the very loud bang, which we had. Here it's a tiny crack. In lightning, huge, 20,000 degrees centigrade, 43,000 thunderstorms daily on this planet. A huge, huge number. I'm now going to show you very quickly. We'll just cut things off to the end. So that's what causes the thunder. And during this, we have these chemical reactions taking place, which give rise to nitrogen dioxide. Hang around. We're going to do just this. That's the next one there. No, we're going backwards. Sorry, wrong way. Sorry, silly Szydlo, I'm pointing. Those are the two chemical reactions that occur when lightning strikes. Now, nitrogen dioxide gas and ozone are produced in the atmosphere. Now, I have an experiment here which doesn't take very long, but it's extremely beautiful. In this experiment, we generate nitrogen dioxide in tiny quantities. And actually in large amounts, huge amount. I've got copper in here. I've got water containing sodium hydroxide and phenolphthalein and ammonia in the last. I'm going to pour, now watch, dear children, because when there are thunderstorms, this gas is produced. You don't see it as a dark brown gas. You see it, you never see it because it's very dilute. But this gas is acidic. And this gas will make this purple. So this is produced during the this nitrogen dioxide. This is acidic, turns phenolphthalein colorless. This in turn is reacting with ammonia, which makes that color. Now, while we're doing that, we'll now set up the last experiment. So we're coming on to the, I wanted to do hydrogen. Hydrogen is this is the last experiment. Carry on watching this. There are a remarkable sequence of reactions here. Copper makes copper nitrate. There's nitrogen dioxide here. This is acidic and that's got ammonia. Very shortly, that will start cooling down, and these two waters will get sucked back into there, and you'll see a spectacular range of colors develop in this copper nitrate there, which I won't bother explaining, but it's great fun. Now, what I'm going to do, and I invite you, because the colors are really very, very beautiful. Dear children, hydrogen is present. Hydrogen, the lightest gas in the universe, is present in one of the products of when wood burns. And so it's appropriate to show you how hydrogen burns and in air. When hydrogen burns in air, it simply makes an orange. It is nothing that loud. This is not at all loud.
No, cover your ears still.
It's a beautiful orange flame. This is pure hydrogen burning in air. It's not worth talking about. That's it. Now, this here, by contrast, dear children, this here, by the way, we're watching this, children, watch carefully. We're now sucking back, we're cooling down. This is now sucking ammonia through here, which is alkaline. Phenolphthalein goes pink again. This now gets sucked, watch carefully. This nitrogen dioxide dissolves with great rapidity in water. And so this is sucked from there to there. This one gets sucked from there to there. And watch the beautiful sequence of colors, which you'll see there. Now, while that sequence is going there, I'm now going to set fire to the balloon. I'm now going to set fire. Now, this, children, this is what Pilatre de Rosier, the French scientist, used to call aria tonante, thunder air. This makes a very loud bang. It's a mixture of hydrogen and oxygen. So close your ears. Here we go. Here we go. So that's the mix. Now, final experiment now is the trough. We now have the final experiment. Dear children, watch these colors develop. During this final experiment, we shall be creating real thunder and lightning in here. And I'm going to ask you, can we have the trough? Oscar, leave that. Watch these colors. They're very beautiful. We'll have a butcher's at them afterwards. I'm now going to create for you real thunder and lightning here. And at the end of this thunder and lightning experiment, children, I'm going to ask you to be completely silent. And I'll tell you why. This is not that terrifying, by the way. Actually, it is, but we pretend you're all scientists here by now. I've won you over, so you're not afraid of anything. Now, what we're going to do, can we take the distillation away, dear Oscar? And get me if you can now get me the gun cotton. Here we are. I'm going to, I have 2 balloons here. I'm going to wear this, by the way. This is my special safety mask. I'll tell you why. This is in case we have a flashover, not a flashover, but a flash powder. Now, what we're going to do here, can you see how beautiful these colors are? You're going to have 3 layers there. Now that needs to be much lower. The balloon needs to be sitting right on there. We'll do that in a second. We'll just do that in a second. Now, what we're going to do here, children, and this is the very last experiment of the day. Yeah, just keep taking away. Oscar, could you please keep tidying things away? Very last. And I'm going to put the slide. The last slide is here. Now, this is today's summary. This is what you've learned today, is that when wood burns, there are 2 separate processes, pyrolysis and combustion. Combustion is oxidation, pyrolysis is thermal degradation. Please remember, that's the only thing you have to remember. Now, we're going to have to put these balloons down in a minute, and we need to tie them. I'll tell you what, Andres, if you can, that's it, just make them lower, that's fine, that'll do. These are balloons filled with a mixture of hydrogen and oxygen. They're going to be the thunder. I'm lying here, a rapidly burning fuse, which is known as... What's happened? Did you burst it? Ah! Too bad, we'll just have one. It does happen to the... You see, even in a hurry, even the best scientists... Don't worry, children, we'll have one. It'll be perfectly good. One is better than none. Now listen carefully. Now listen carefully. Listen carefully, children. One is fine. That will make a little bang. That will make a pretty loud bang. It's not that loud, but it's not the end of the world. Now, what I'm going to do here, can we take away the gun cotton now? Can we take away the box with the gun cotton? I'm going to quickly make up 2 flash powders here. And what's going to happen? I'm going to set off we're back to our campfire that we had at the beginning. The campfire at the beginning, do you remember I poured some liquid onto a powder? I'm going to do the same here today. The liquid the powder which we use is potassium permanganate, and that's what my secret with my Scout success was. And the liquid we use is going to be glycerine. And that's what you put on, that starts burning. And once this has gone off, there will be a loud bang and 2 flashes. I would ask you all to be completely silent. And I'll tell you why. Because we're now going to return to the sociology of our campfire. We're going to return and we're going to hear the traditional melody that is played at the end of all campfires where many people gather together. And I'll ask you to listen carefully. And after that, I will be very, very happy to take any questions. So this is the final experiment. After this, please remain completely silent. It's not going to be that dramatic because one of our balloons has now floated up to the ceiling. I'm making up here, by the way, and I'm having to having to take great care here. I'm making up a flash powder, which basically enables makes it look as if it's a real lightning. It's like real lightning. It's a high intensity. It's magnesium mixed with potassium chlorate. It's a high intensity ultraviolet light of the same type that's given out by real lightning. Obviously, the amounts, this will make a flash go up into the sky. There will be one flash here, and there will be another flash. So this is going to be thunder. This is a lightning flash, and this here will be another lightning flash. Oh, let's hope it works. You know, this is all a bit of a thing. I think we'll just sprinkle this liberally everywhere. Damn it, I can't waste chemicals. Now then, this goes into the bin there. Now, so, dear children, please listen carefully. The flashes are really very bright indeed, so you shouldn't be looking at them directly. The bang, you've already heard one, so this is not going to be any louder, but it will be a bang. So that we are about thunder. Please look at this beautifully. Please look at this beautifully.
Sorry, Andrew, can I just interrupt a second? The bang will be a lot louder. This is a hydrogen oxygen balloon, so it is essential that you have your ears covered with your hands, not your fingers. When Andrew does it. Thank you, Andrew.
Okay, thank you very much. Children, I hope you're all ready. Thank you very much. Now listen carefully. I'm going to pour on. Actually, I can take my goggles off because this isn't dangerous, actually. The earlier one was dangerous, this isn't. I'm going to pour this on, and it will take approximately a minute. Now, the important thing is, please remember, complete silence once this has finished. That's the important thing. It will burn, there will be a couple of flashes, hopefully a bang, and I've got my fingers as well, because I want you all to feel that we're safe.
With your hands, not your fingers, please.
There, like this, like me, like this. So here we are, hopefully it'll work. And then complete silence when you'll hear the final tune of the day. The fire is burning and going, and we're waiting for the final tune of the day. Thank you very much for your attention. I wish you all a very, very good evening. Thank you very, very much indeed. Can I call Andres? Andres to the floor. Thank you very much. Andres, my assistant. Oscar. Musicians. Musicians. Can I have the musicians, please? Thank you very, very much indeed. Thank you very, very much indeed. Musicians. Philip. Thank you and a very, very good evening to all. Thank you so much.